Right, so now we have performed a new simulation study. So to start the simulation, we go here to the selection here and we have a simulation. But if you don't have this option, you can go to add-in and you select Solidworks simulation and you click OK. All right, so here we are going to run a new study. So we go to new study and and here we click the study or the simulation menu and we select a static and we name it. And we name it as a static. Then you click OK. And now we are going to apply the material. You click the material in the simulation menu here, and we are going to select AISI 304 from the steel folder, AISI 304, and then we click apply and close. All right, now after we have applied the material, we are going to define the fixed restraint. So in the simulation study tree here, you right click fixture, and we select a fixed geometry. And we are going to select the face to apply the restraint. And then this is the face that we are going to apply the fixed geometry here. And after that, we click OK. And then we rename it as a fixed site. And then we are going to define the force. So we rotate the model to reveal the face with the 100,000 and 110,000 Newton tensile force is to be applied. And we are going to select this face here. So you right click at the external loading, and we're going to select a force. And then from here, in the type area, we select a normal. And in the units, make sure that we select the SI, and the force value will be 100,010 Newton. Then this is the face that we are going to choose here. So this is a compressive loading. What we need to do is we select a reverse direction to make it a tensile loading. Then we click OK and we name it as a tensile force. Right, so now we are going to run our analysis here. We right click the study icon here. So we go to the design tree here. Click, select run. Now, so we have the result here, and we can see after the analysis is complete, Solidworks simulation automatically creates the result folder with the default result plots that we specified in the beginning of video. We have stress 1 meters here, and we have a displacement, and also we have a strain here. Then we can delete this one here. So now, as we double click on the stress one, under the result folder, we can see the plot here, and we can see that the stress plot is in megapascal unit, and the legend features scientific numbers with a 6 digit. And here we can observe that maximum value of 1 meters stress is 4.8 megapascal. Which significantly exceed the yield stress of our material. We have the yield stress of our material here is 206 megapascal, as indicated by the red marker. Right, so now we want to create a section plot. Yeah, as in many applications, it is useful to cut the model and look at the distribution of the result and quantity into thickness direction. So what we are going to do, we go to the result here, we right click, we select as 1 meter stress, and we right click and we go to section clipping. And then from the Solidworks fly out menu here, we are going to select right plane. Select right plane. Then for the distance, we select 30 millimeter, and the rotation X, maintain it at 0 degree. And for rotation Y, we select 15 degree. And we can also use a reverse clipping here to change the direction. Also, we can select the clipping on off here to control the to disable the section plot. So I'm going to close this section clipping here for now. Right, so now suppose that we wish to display a portion of the model where the von Mises stress is between 170 megapascal and 275 megapascal. So what we have to do, we go to the result here and we right click on our stress here, the von Mises, and we select the ISO clipping. Select the ISO clipping, and this open the ISO clipping property manager, as you can see here. And in the ISO value box under the ISO number 1 here, we enter 275 megapascal, and we check on our ISO number 2 here. Here we select, we type 170 Newton per millimeter squared or megapascal, 105 here. And we click OK, and here we can see that we have a 2 black arrow here on the stress legend that indicate the values defined for the 2 ISO surfaces. And alright, I think that's all for if you want to create the ISO clipping. I think we can add another one here. I think if you want to reverse the clipping direction, you can select this one. So from here, meaning that here we can control the cutting direction. And if you want to reset the plot, we just click clipping on off here. Alright, so now we want to prop the stress result from the part here. So you right click on the stress, right click, and we select prop. And using the pointer, we click the desired location on the plot here. It helps if you zoom into that area. And I just select a point here, point here, point here, 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 here. So we have select, you can select any point here. So I have selected 1, 2, 3, 4, 5, 6 point here. And the stress result are listed in the result dialog here. And in the plot, the selected location. And under here, we have a report option where you can save the resultant file, plot the path graph, or save the location as sensor. And if you select this graph here, this plot here, we can see that this figure shows von Mises stress path plot for the selected location that we have selected on the figure here. And now we want to define a displacement plot. So what we want to do here is we go to the result and we double click the displacement plot icon here. Then from here we can see that the displacement shows a maximum resultant force of 0.1435 millimeter. And also we can animate the displacement plot. To animate the displacement plot, just right click on the displacement and we select animate. And here in the animation property manager, you can start and stop the animation. And also you can set the number of frames here. You can also control the speed. And also you can save the animation as an AVI file. Right, so now there are several other post-processing quantities available to view at the end of our analysis. For example, we have a factor of safety of the design based on the design strength of the material. And we can do that by right here, go to the result, and we select define factor of safety plot. And just select all. Then we click OK. Then here we can see that the minimum is the minimum factor of safety is equivalent to 0.51, and the maximum is 21.05, right? So what does it mean here is that typically the factor of safety below 1, meaning that the model is failing or not strong enough in that area under given loading condition. Yeah. So next we are going to perform a fatigue check plot. Fatigue check plot can serve as a quick indicator if the fatigue may be of any concern in the design of the component. So to do that, we are going to the right click on the result here, and then we go to define fatigue check plot, and then we set the loading type to on-off loading to indicate that the tensile force may oscillate between 0 and 110,000 Newton. And we select, we set the surface finish factor to machine, and we keep the loading factor and size factor at the default values of axial and 0.75. So here we change the axial and machine, right? And under the material, we keep the scale, this value and minimum safety factor, fill at the default value of 1, and then we just click OK. So here, what we can see here, we have red areas, and the red areas indicate potential fatigue problem. Yeah. And finally, we are going to generate report in Microsoft Word format. So how to do that? We go here, we select report. And then under the report section, we select the required report parts. For example, we can deselect the option content information. We can deselect this, deselect the option content information, as we do not have any in this analysis. And if you want, you can enter your hidden information, and we click publish. Right. Right, so now we can open the report in Microsoft Word, and when we open the report, we can examine the result. So this is all the result in Microsoft Word document.